Given, you have 2 identical eggs and a building with n floors labeled 1 through n from bottom to top. There is a hidden critical floor F, drops above F break the egg, at or below F it survives. Each move drops 1 unbroken egg from a floor you choose, a broken egg cannot be reused. Return the minimum number of moves needed in the worst case to know F for certain. Example 1, n equals 2. Drop the first egg from floor 1. If it breaks, F is 0. Otherwise drop the second egg from floor 2. If it breaks, F is 1, if both survive, F is 2. In every case we learn F within 2 moves, so the answer is 2. Example 2, n equals 100. An optimal plan needs at most 14 drops in the worst case, for instance by probing with the first egg at floors 9, 22, 34, and so on, then using the second egg 1 floor at a time inside the surviving interval. Output 14. You have a 100-story building and 2 identical eggs. You need to find the highest floor you can drop from without breaking, in the minimum number of moves. Your immediate instinct might be to split the building in half and drop the first egg from floor 50. But if it breaks, your strategy instantly shatters. With only 1 egg left, you have no safety net. You are forced to test floors 1 through 49 step by step. In the worst case, if the critical floor is 49, that is 50 total drops, which defeats the purpose of an optimal strategy. Here is the ultimate breakthrough: an optimal strategy must assume the worst-case scenario will happen. To make our worst-case performance identical no matter which floor is the breaking point, we need to balance our risk. If egg 1 survives a drop, we have used up a turn. To compensate for that spent turn, our next floor jump must be exactly 1 floor smaller. We are trading egg 1 drops for potential egg 2 drops to keep our total cost perfectly flat. Let's call our target number of total moves x. For our very first drop, egg 1 jumps straight to floor x. If it breaks, egg 2 checks the x-1 floors underneath it. Total drops? Exactly x. If it survives, we have x-1 drops left in our budget. So, egg 1 leaps forward by x-1 floors. If it breaks there, egg 2 sweeps the new gap. Total drops? Still exactly x. Every single time egg 1 survives, its next leaping interval shrinks by exactly 1 floor. If we sum up all of our shrinking intervals, they must stretch to cover or exceed our total number of floors, n. This sequence is nothing but a classic triangular number series. The math simplifies beautifully, we just need to find the smallest integer x where the sum of numbers from 1 to x is greater than or equal to n. We have turned a complex dynamic programming problem into a simple algebraic triangle puzzle. The triangle gave the fast 2-egg answer. Here is the decision rule behind it. 4 floors, 2 eggs. What if the first drop is from floor 2? If it breaks, this drop plus every floor below costs I moves in the worst case. If it survives, the floors above become a subproblem, same 2 eggs, but only f-I floors left. That subproblem costs 1 plus dp of f-I moves in the worst case. Max means prepare for bad luck, take the worst of I and 1 plus dp of f-I. Here f is 4 and I is 2, max of 2 and 1 plus dp of 2 equals 3 moves. Min means pick the smartest trial floor, try every I and keep the smallest worst case score. So dp of f equals the minimum over I of max of I and 1 plus dp of f minus I. First, the closed-form math solution. Find the smallest x where x times x plus 1 over 2 is at least n. Multiply by 2x squared plus x is at least 2n. At the boundary, x squared plus x minus 2n equals 0. Apply the quadratic formula x equals negative b plus the square root of b squared minus 4ac, all over 2a. Here a is 1, b is 1, and c is negative 2n. That gives x equals negative 1 plus the square root of 1 plus 8n, all over 2. Plug in n equals 100. Take the ceiling of the positive root, the smallest integer x is 14. The same dp recurrence from intuition fills a table in n. Fill the table, at height 6, 2 eggs need 3 moves in the worst case. That matches the jump idea, 1 plus 2 plus 3 already covers 6 floors. We can analyze both approaches, the closed form math and the dp table. Closed form, time is O of 1, plug n into the formula and take a ceiling. Space is O of 1. dp, time is O of n squared, for each height we try every trial floor. Space is O of n for the table. First, pseudocode for the closed form math solution. Build the discriminate 1 plus 8n, take the positive root, and return its ceiling. Next, pseudocode for the dp recurrence. For each height f, try every trial floor I and store the minimum worst case moves.